So, in talking about electric fields, one of the representations that we often use for displaying an electric field or for trying to show the electric field that we want to get comfortable with is field lines. And so, what is it? What are field lines, and how should we interpret them? So, there are a couple different rules for sort of thinking about field lines. The first one is that at any point, the direction of a straight field line or the direction of the tangent to a curved field line gives the direction of the electric field at that point. So one of the things that we'll be able to do is basically use the lines themselves to figure out the direction of the electric field at points along the line. And then two, the field lines are drawn so that the number of lines per unit area is proportional to the magnitude of the electric field. Well, what does that mean? Basically what that means is where you've got a lot of field lines drawn close together, you have a very strong electric field. And where your field lines are very spread out, you have a weak electric field. And then lastly is that electric field lines extend away from positive charge and towards negative charge. Another way to think about this is that electric field lines originate at positive charges and terminate at negative charges. So how do we use these rules then? Well, so let's think for a simple positive point charge. And we've said that the electric field is a vector field, which basically means we know that we can go anywhere in space and we can calculate what the electric field vector is supposed to look like. And so here that's been done over a whole host of places. And so one way to represent the electric field due to this positive point charge is like this. Just sort of show what the vector is over and over and over and over and over again. But what field lines allow us to do is basically say, instead of having to draw a whole bunch of vectors, we can get basically the same information by drawing a handful of field lines. And so what you'll notice is here I've taken exactly the same positive charge, and now I'm representing the electric field in terms of field lines. And so you'll notice that my field lines point away from my positive charge, that these field lines are clustered tightly near the charge. They spread out when they get away from the charge. So that tells me that A, the electric field due to this point charge points away from it. That's good. That's what I know has to be true for positive point charges. I know that the electric field is large, relatively large, close to the point charge, because the spacing between my lines are fairly close here. It gets weaker as you go out because basically the gap between lines gets bigger as you go further and further out. So this tells me that I have a radial field that gets weaker as it goes away, and in this case happens to point, sure enough, away from my positive point charge. If this were a negative point charge, then I could represent it with the same set of field lines, just they would all point in rather than away, because I know that again my electric field points towards a negative charge and away from the positive charge. So with this idea we can represent sort of increasingly complicated electric fields. So here are two examples. In this case, here's an electric field due to two similar charges. So here I've got two positive point charges. And so you'll notice again that the electric fields clump together near the charges. So I have a strong value for the electric field when I'm close to one of the charges. And then there's this big gap here in the middle, and sure enough, that's where basically the field from each individual point charge is mostly canceling each other out. And in fact, right here in the exact middle, it's perfectly canceling each other out. As you get sort of on the far side of the point charge, basically it just sort of looks like a normal electric field due to a single point charge, mostly because as I come farther and farther away, the electric field really doesn't see two slightly separated charges as much as it just sees two charges, or two positive, or a single charge here in the middle that's twice the magnitude of what these two are. The second field that we've got here is the field due to our dipole. So again, I've got positive charge and negative charge, equal amounts, separated. So here's my little dipole, my dipole moment vector that we were talking about in class would run in this direction, right? So from my negative to my positive charge. And again, you can see that here, where the field is the strongest, is actually right here in between my two charges. And between my two charges is the point where the field's really sort of adding up. Right? If I were to think about what's going on with the field right here, well, it points away from my positive charge and towards my negative charge, and so along this line they're actually adding together. And so when they're close to this line of symmetry, they're mostly adding together, and as you get farther and farther away from that, what you have is those components start to sort of disalign themselves so that the piece that's canceling out gets larger and larger, and so the field itself gets weaker and weaker. So again, you can, with our field line diagrams, you can look for places where the field is strong, you can look for places where the field is relatively weak, and they're always going to indicate direction. So again, you see that here my field lines all point away from the positive charge, all point towards the negative charge. And so if you picked any point you want, say this point right here, so here is your field line as it curves around, so the tangent to that point, the tangent to the curve at that point in the direction that that field line is running, so in this case basically downward, is going to be the direction of the electric field. So that's the idea. So we'll use field lines a lot as sort of an easy way to indicate, or an easier way to indicate what's going on with the electric field.